Okay, black holes are not just giant vacuum cleaners that suck in everything all at once. There's a lot more to it. Hey folks, welcome back to the Deep Cosmos. This is Devin here, and I know firsthand that astrophysics can be a lot to get into. There's so many different things to explore, from black holes to stars, from galaxies to the search for life on exoplanets. And this, combined with a shirt that my girlfriend got me, gave me a really good idea. What if I went through the A to Z of astrophysics, going through the alphabet and the universe to give you all a good gist as to what astrophysicists study and what I aspire to study for the rest of my life? If you want to follow along on this astrophysical journey, please hit that subscribe button and give me a comment as to what other astrophysics topic you want me to talk about on this channel. And now for our first letter, A, for accretion. What exactly is accretion? What does that word mean? It's really just a fancy word for how black holes eat stuff. Not to be blunt, but that's pretty much what it means. For a less blunt definition, it's how black holes gain mass from absorbing outside matter. Before we move on, I want to define what a black hole is here so we can get more of an idea as to what kind of object we're talking about. A black hole is this immense gravity well that is so gravitationally powerful that not even light itself can escape. And light has the fastest speed in the universe. This means that beyond a certain point around the black hole that we call the event horizon, light coming from beyond that point would not be able to come out of the black hole. So anything emitting light, like some sort of flashlight, we wouldn't be able to see. If you want more of an in-depth definition of a black hole, just wait until my next episode, because the topic for the letter B is black holes. Okay, so now that we have some common ground, I want to get one very common misconception about black holes out of the way. Usually in media or in sci-fi movies, black holes can be depicted as these giant cosmic vacuum cleaners that just suck in everything immediately, or they are portrayed as some giant sinkhole in outer space. That's simply not true. Why is this not true? It's because pretty much everything in the universe has some sort of inherent rotation to it. Or in physics terms, everything in the universe has some sort of what's called angular momentum. We see this inherent rotation across the universe. Our planet Earth, for example, that rotates. The sun rotates. The planets orbiting the sun go around the sun. Even our galaxy, everything in our galaxy orbits around the center. Everything has that inherent rotation, and there's no exception to this with black holes. We call these rotating black holes Kerr black holes, after the New Zealand mathematician Roy Kerr. What does this mean for objects falling into a black hole? It would mean that they wouldn't just fall straight in. They would come in and start to orbit around the black hole, and then slowly but surely spiral inwards. So if you were to make a comparison of a black hole to something on Earth, it would be a lot like a whirlpool that we see in oceans, and you can do it in your very own kitchen sink. If you plug the drain and fill your sink up with a certain amount of water, not overflowing, of course, and you unplug the drain, you would see the water flow into a whirlpool. The water going around in circles, right, slowly but surely, until eventually it's funneled down and falls down the drain. This same process happens with black holes, with objects and debris coming into an orbit, circling the black hole, and spiraling inwards towards the center. Now, this should come as no surprise to any of you, but in order for a black hole to accrete and gain mass, there needs to be something there for the black hole to accrete in the first place. There are probably examples out there of black holes that are all alone, with nothing to use to gain mass and accrete. But there are also plenty of examples that we have observed where there is a black hole and something else orbiting around it for the black hole to gain mass. For the case of smaller black holes, or what we call stellar mass black holes, or the mass relatively of stars, we see that there is a black hole and a star orbiting around each other. And the black hole, like I mentioned before, has immense gravity. So we see cases where the outer mass of the star is stripped away and brought towards this black hole and eventually is sucked in, kind of like a vampire sucking in blood. And that is why we call this orbiting star a donor star. For much, much larger cases, we have supermassive black holes that reside at the centers of galaxies. And there they have huge clouds of gas orbiting around the black hole and going through the process of accretion, very slowly but surely falling in. Now, in either supermassive black holes and stellar mass black holes, we see that as you get closer, the material that's falling into the black hole forms what's called an accretion disk. Not a cloud, a disk as you get closer in. This is due to the conservation of angular momentum, which is what I briefly mentioned earlier. An example of this conservation of angular momentum can be seen in the formation of our solar system. We're at a point now where the planets and the asteroid belt and even the Kuiper belt sits pretty much in a plane or disk. When the solar system was first forming, it was this cloud of gas, but over time, when things rotated and settled in, they formed a disk because of this inherent rotation and conservation of angular momentum. Now let's focus in on the accretion disk itself and talk about what's actually going on. In the case of a stellar mass black hole with a donor star, the mass from that donor star comes in and forms that disk around the black hole. And these particles are moving really, really fast, and they're rubbing against each other. There's some interactions going on, and this causes a lot of heat. This is similar to rubbing your hands together, right? From the friction of your hands rubbing together, you get this heat. And of course, with heat can come light. Astronomers can use this light coming from the accretion disk to observe and even find these kinds of objects. It gets to a point where these particles are moving at what we call relativistic speeds. These are speeds that are comparable to the speed of light. Obviously less than the speed of light, but comparable. When particles such as electrons around this black hole get to these relativistic speeds, we get to a point where we can call it more of a corona around the black hole. This is because you're having interactions with these particles, not only with each other, but with that light coming from the disk initially. So now if things are getting scattered around the black hole, but are also still bound to it by its gravity. The kind of light we see from these interactions are primarily X-rays. It finally gets to a point where the particles get so close to the black hole that they cross what's called the event horizon. And like I said earlier in the video, beyond that point, we don't know what happens to the particle other than it falling into the center of the black hole. This entire process, from particles coming from a different source, coming into the accretion disk and slowly but surely spiraling inward to the center of a black hole, depends on the size of your black hole. If you're talking stellar mass, it's on the order of days, maybe weeks. And if we're talking supermassive black holes, this could take years for things to fall in. Now, I do want to briefly mention that in terms of accretion, anything that's gaining mass can be accreting, right? A planet in its formation could be accreting debris to form. A star could be accreting mass. That's the same thing. But in terms of what astronomers study primarily, like which accretion process is the most important to study, it's going to be black holes by a landslide. The last thing I want to talk about with accretion is if that particle were turned into an unfortunate astronaut falling into a black hole, because this process is crazy when you run it through the equations. For this, let's assume a feet-first dive for this astronaut. And at this point, they are beyond the event horizon and getting closer and closer to the singularity, right? Spiraling in, this very, very thin funnel, okay? It gets to a point where the gravity difference between this astronaut's feet and this astronaut's head is significant. If you're back here on Earth, we don't notice it, right? Earth is huge compared to humans. So the scale from the gravity difference from our head to our feet is pretty much nothing. We would not feel it. But take this idea to a black hole, and as this astronaut's getting closer and closer to the singularity, the difference in gravity between your feet and your head is significant at some point. So, what's the consequence of this? The astronaut just begins to stretch, right? Slowly but surely. Just like a typical morning stretch, right? Not too bad, but it doesn't stop. It keeps going and going and going and going. So much so that finally the molecular bonds between your skin, your bones, your flesh, whatever it is, cannot take it anymore, and you split into two. And eventually, those two ends split themselves, so now you have 4 pieces, then 8, then 16, then 32, and so on and so forth, until your body becomes the string of atoms. And this string of atoms, as you're being stretched and broken, is going around, being funneled, and brought down to this infinitely small point, which is pretty much an infinite nothingness, forever. Now, one might ask the question, what is this excruciating process called? It's called spaghettification, because you become this noodle of atoms falling into a black hole. A pretty appetizing name for an agonizing end. Oof. There's this really cool rhyme that describes this process really well, written by astrophysicist Neil deGrasse Tyson, and I want to end on this because it really gives a great idea as to this excruciating process in detail. Okay, here it is. In your feet-first dive to this cosmic abyss, you will not survive because you will not miss. The tidal forces of gravity will create quite a calamity when you're stretched head to toe. Are you sure you want to go? Your body's atoms, you'll see them, will enter one by one. The singularity will eat them, and you won't be having fun. Think deep, folks. See you next episode for B for Black Holes.